Hey, hey everybody. So, as I mentioned on Tuesday, today what we were going to do is take a look here at our second example. This is 2.bin in the buffer overflows example folder. And this one looks a little bit differently than number one. I mean, it looks similar. We got the same main function essentially. It's just that instead of the no way to possibly get here function that prints out a what appears to be a root shell for us. Instead, we have some random thing function, and then an int, my favorite number, and that favorite number equals 58623. Now, as I mentioned last time, what we're going to be doing is what I'm showing you here with this example is how essentially we can find code or instructions just about anywhere in an application. Whether or not we have useful instructions, well, that's another matter entirely, but basically data is data, and it's all in context and how it's interpreted. Now, the intention here by the programmer is that this would be an integer, 58623. And that integer, I mean, apparently wouldn't be used for anything, but, in the case of an actual real life example, it could be, used somewhere else for any other purpose in terms of the application itself. It doesn't really matter. The fact that the value is there alone is exactly what we're looking for. And the reason for that is because in the context that the programmer intended, it is to be interpreted as an integer. But we can alter that context and have it considered to be a different type of data, like an instruction. So let me show you how this works here. All right, so here we are in Ghidra. This is 2.bin that I've imported here. And if we go to our main function here, as we mentioned before, here's our decompiled code. This is just pseudocode. This is just Ghidra's approximation, right? Based on the syntax of the detected language. That's really it. This is the instructions that Ghidra interpreted. And as we talked about before, memory offsets and then direct hexadecimal translations of the binary of those instructions, which, when we convert that binary to assembly instructions, matches patterns for the actual movement of data in this case. So a sub RSP hex 10 in binary would be the converted hexadecimal strings here. If we went from hexadecimal to binary, that's what it would look like. And if we come down, we can see that a return, for example, is a C3, a leave is a C9, and so on. Now, the number that we have here, the number that we have here is obviously a decimal number, right? It's an integer. It's not there's no decimal place in there. It's not a float or a double, but I mean, it's in decimal encoding. So hex, decimal, and so on, just different ways of representing data. Does Ghidra have a programming calculator? Yes, it does. All right, so our decimal format here is 58623. Oh, it does have it right here. So if we convert that to hexadecimal, it's E4FF, or in binary, and more or less like that. It's a much longer string than can be represented here, obviously, but yeah, that's pretty much what we're dealing with here. So that decimal and this hexadecimal are equal. They're the exact same data. So that means that if we can, let's look here for a bit. See if we can find maybe a similar function. We're looking for E4. So here's the number, right? D-word pointer RBP plus local C, which is hex E4FF, or 58627, the number that we have here. So that's even here right now. But what I'm looking for is looking for a jump. Because what we want is a code trampoline. So a jump command here. Then I'll have to show you another way here. Let's go to the... all right, so there's a link on Canvas under Application Attacks Overview module. The last one is an x86 assembler that takes you to diffuse.ca's online assembler. I'm just going to show you essentially what that means. So as we see in Ghidra, our instruction here in some random thing that does that assignment of an integer is a move D-word pointer, so RBP plus local C, which is hex E4FF, which is the hexadecimal conversion of the integer 58623. And if we copy those instructions and we put them into our disassembler and disassemble them, indeed, I mean, that is what we see, right? The move instruction that we just saw. But we know that this is the representation of our digit, and if we just take those instructions, the FFE4, and remember, it's FFE4 because it's little endian, so the basically the second byte is loaded in before the first byte here. And if we put those into our disassembler and see what they translate to, well, that literally translates to jump ESP, which means we have a code trampoline, right? We all we need to do is, instead of doing what we did for the first example and calling the memory offset for the top of a function, is we just need to drop instead into the middle of this instruction here. And if we can hit that memory offset, then it will execute that as if it were, it's going to interpret that as a jump ESP. It doesn't have the context of the data that came before it, so it doesn't know that it's a move. It's just interpreting in this information. So where are we at here? What memory offset is that? So here we have 40117E, 40117F, 401180, 401181, 401182, 401183, 401184, and then here we have 85. Okay, so this is EF0, 1, and 2. So 81 and 82 are the 2 bytes we have. Now, what we just did is sort of the manual way of doing this, and you certainly should know how to do that, how this works. But just so you know, there are automated tools that we can use to scan for these sorts of things, these code trampolines. What we just did is return-oriented programming. The most basic form of it, but that's what we just did. And there's a tool that helps to look for these ROP elements, or these instructions, these code trampolines. It's called ROPper. It should be installed according to the instructions. Let me see if I've got it. Apparently not on this machine. So apt install. I will grab it quick. Oh, God. Okay. Now I've got ROPper. So you can use ROPper here. to look for these elements of ROP chains. I forgot the syntax. Gadgets. That's what these little elements are known. When I say that this was the most basic form of doing this, it's because we found a jump RSP, which is about as perfect a ROP a gadget as you can possibly find. It's as direct as you can get because it's going to jump you right back to your shellcode. But sometimes we need to assemble multiple instructions in order to manipulate data or get to our shellcode, and that's why it's called a ROP chain. When you chain gadgets together, like for example, your first instruction is a jump. I don't know, a jump RAX, and then we change the value of RAX with another instruction. Like for example, well, okay, let's say that we are able to put a number into a register, and we need to do a mathematical operation on that, add or subtract, in order to reach the actual offset that we need. So our first element of the ROP chain is like an add or a sub. Then we have maybe a jump to RAX, and that jump to RAX leads to another gadget, which is a jump ECX, and then the jump ECX gets us to the stack pointer or base pointer, and so we had to chain a couple of those gadgets together in order to do this. No binary loaded. Okay. File. It's been a minute since I've used Ropper, so please bear with me. All right, so file, and then the binary 2bin elf x8664, and now we should go gadgets. There we go. So I just ran a raw gadget scan on this, and these are all of the gadgets that I got back from a scan of this very, very simple program. And you can see it even will do some of the chaining here for you in order to get our return. Again, return-oriented programming, ROP. So for example, in this chain, if we pop RSP, pop R3, pop R14, pop R15, then we get a return here at the end. We don't really even want a return right now. We were just looking for a jump ESP or RSP. And I mean, like here is one, right? And this is very close to where we actually found this. It's just that it's at 8.0 because it also includes this CLD command here. So here's 8.1 and 8.2 exactly as we found. They're listed in order of their offset here. But do we have any other candidates that perhaps we could have used? I mean, here we got a NOP and return. So for example, here we have a move to EAX. That value at that instruction pointer offset, test RAX, so compare the two, and then jump if equal. So if we can make RAX, well, jump equal will always be true, or no, JE 1016, then call RAX, and we could maybe go from there. But I'm looking for another like good candidate that we could easily have used without getting too complicated. Honestly, not seeing any. All these are super long. Add RS. Oh, here we go. Here's one. Add RSP8. So if we sent 32 bytes instead of 24, and then had our shellcode. Then had our return. Yes, then had our return followed by our shellcode. Then we could have bounced around that way. Here's just a call RAX. So if we could put our shellcode into RAX, or a pointer to our shellcode into RAX, then we could just use this, and so on and so forth. So this is just a way to not have to manually look through the disassembled code to find useful gadgets. Right? This will help and search for you. And we will be using this again later. We'll get to return-oriented programming about halfway through the semester or so. But let's say I'm looking for something in particular, if I can remember how to search. Well, it did find it, but again, it's the lone instance of there being just a jump RSP. But it did find it, and it did find it at the correct offset. So if we had just loaded this into Robber and did a search on jump RSP, yeah, it would have found our exact address. And it found this, of course, even though that isn't an actual instruction. It's just incidental to the assignment of that integer. So now that we know what our offsets ought to be, let's take a look at the Python script here. All right. So this time in Python, we're doing something a little bit different. Oh, and I also should mention, I suppose, at this point, I don't like lectures that I post online to be too long. There's plenty of studies that show that people just kind of stop paying attention after about 20 minutes. So even though normally we would spend about 2 hours on this, well, it'd be about an hour on this and then another hour of continuing our lecture. I'm just going to do just this, just the example here, and I'm going to save the lecture for Tuesday. I just don't want to have too long of a video. It's not worth it. All right, so we can see in our example what we intend to do here. We're going to have to break it down a little bit. First of all, we're, of course, importing Pwn from Pwn tools. We're importing Pwn tools. Then we identify our architecture. This is important because, again, registers are different for different architectures. R registers, E registers, and so on are only available in certain architectures. I mean, technically a 64-bit architecture does have access to E registers and so on and so forth, but certainly on a 32-bit system you can't access R registers. Then we have our jump RSP. Now, notice that when we did our translation here, it was jump ESP. Well, that's why it's so important that we identify our architecture, because we're actually going to be jumping RSP as the register would be known in 64-bit, so we identify it as a 64-bit binary. Here is the memory offset we just calculated, so we know that FF is at 8.1, E4 is at 8.2, so we want to jump to the first address there, 8.1. Then we are going to use Pwn tools to generate assembly code, or to generate shell code in assembly for us. This is one of the best parts about Pwn tools, is you don't have to look up and package your own payload. You just have to know how to craft your payload for your program. So shellcode in this case is going to equal assembly instructions, and we're using shellcraft targeted to AMD 64 architecture for Linux because it matters, and then shell, sh shell. So if we wanted to inject a command, we could do that here, and it would create shellcode to inject a command, but in this case we just want to pop a shell, so we're just calling a shell. Once again, we're going to do P for process, but remember, if we were attacking the lab machine, we would want to do a remote here instead of a local process. And then here, again, is our payload, as it is. So we know that we have an offset of 24, because it's the same exact code as example 1, and we already calculated how far we have to go for that one. It's the same code, 16 bytes plus 8, so 24 bytes in order to get to our return address. But now, instead of inserting the return address to another function, we're going to insert the return, we're going to insert a return address of basically the middle of that instruction declaring that integer, and we're going to remember to pack it 64-bit. Then we are going to append our shell code, and then we're going to terminate it. So what's going to happen is that we are going to RSP is our stack pointer. So what's going to happen is we are going to get to our return address. It's going to jump us up to that function, and that function is that instruction at the declaration there for the integer is jump RSP, which means that we're going to jump up, we're going to see that instruction, we're going to jump back down, and we're going to land right at the top of our shellcode. And then it's going to execute it as if it were the next line of code. And then we're going to drop into an interactive shell. All right, so let's well, first of all, let me get back to the right folder. So first, actually, before we run this script, let me just execute 2.bin just so that we can see how we normally would operate it. Of course, it's the exact same thing we saw before, so there's nothing new here. All right, so now let's run our Python script. And there we have it. So I can see that I'm at the red $sign. That means I have a root shell here. Starting local process with the PID, switching to interactive mode, enter some data, and we entered in the A's, and then we have hex 81, hex 11. That's going to be the beginning of our jump RSP. So at this memory address, again, little endian, so 8111. You can see that that's that number that's being entered there. And from there, how about who am I? Well, that's the name of the root account here. Yeah, just like that, we have a working active shell by causing the CPU to essentially hallucinate a jump RSP or a jump ESP command that we didn't actually send it. So that's how that's done, I guess. Okay, I am going to leave it at that then, about 15 minutes or so for this example. I'll leave it up to you to try it yourself now. Make sure you can get this working. And on Tuesday, we're going to go back to our next lecture here, talking about the rest of these basic attack overviews. Okay? And maybe we'll even have a chance to get to some stack cookie examples. That would be fun. All right, so take care, and we'll see you then.